Hello student, welcome to the web optics course. Today we are going to start a new topic which is polarization of light, and we are going to discuss the basic concept of the polarization in this lecture. So, we have lecture number 52 today. And we start a new topic, polarization of light. So, by definition, polarization of light is nothing but the direction of the electric field vector E, and if I draw that, suppose I am drawing an electric field, sinusoidally varying electric field, and that is normally the way we draw. So, in this plane, suppose the electric field is vibrating and this is the direction of the vibration of the electric field. So, if I write this direction as x direction and this direction as z direction, so the E, electric field E in the vector which is a vector quantity, I can write as some amplitude E naught with a unit vector and then cos of say k z minus omega t, that is a propagating wave, and this is the way we represent. When we represent that, then this is the direction of the polarization. This is the direction of the polarization of the electric field. So, E is associated with the plane monochromatic electromagnetic wave, as I mentioned, which is perpendicular to the direction of the energy that is carried, which is z. So, here the direction of the E and the propagation direction which is defined by k is perpendicular to each other. In electromagnetic field, E and B, they are mutually perpendicular. So, if I draw, suppose electric field is vibrating along this direction, magnetic field associated is vibrating along this direction. So, E cross B is a direction along which the energy is flowing, So, E and B, if they are polarized along this direction, then the energy will always be flowing in this direction. So, generally the polarization can be divided in few categories: linearly polarized, circularly polarized, elliptically polarized, etc. But before going to that critical problem, we need to know that the polarization normally, when the source is emitting light, suppose this is a normal source, say sunlight, it is emitting light in all direction. So, electric field that is coming through this light is randomly polarized. It is randomly polarized. So, the direction of the polarized not unique, it is changing randomly over the distance. That is in general the case. So, whatever the light in the real life we observe, they are heavily unpolarized, because their polarization direction is not uniquely defined in a particular direction, rather it is changing over the, all over the space it is changing. So, if I look a random polarized light, so it will be polarized in all possible directions, and pictorially if I show, it will be like this. So, the electric field that is vibrating is showing all the directions. However, if the light is polarized and if I look, so the perpendicular to the screen is the direction along which the light is propagating. So, in polarized light, however, we will going to see a single line, and this is a typical polarization, linearly polarized light. That is the way the electric field is moving. However, there are other categories also, they are polarized, but this electric field no longer will be, they will be rotate in either direction, and that thing we are going to discuss in today's class. So, first let us start with the simple thing, and that is linearly polarized case. Linearly polarized light. So, linearly polarized light, how are we going to define? Let me first draw the coordinate system, because polarization is all about the direction. So, we have to be very careful about drawing this electric field. So, x, y, and suppose this is z. So, electric field, suppose it is in x y plane. So, my electric field, this which is lying in a x y plane. If that is the case, I can write E as two component E x, which is varying with respect to time, and z. So, I can write this as a function of z and t, and unit vector x plus E y, which is function of z and t, y unit vector, where E x component of E is varying with respect to z and t, as I mentioned. So, it can be represented as some amplitude 0x cos of kz minus omega t. So, this is the way it is varying. E y on the other hand, I write a different amplitude for the time being, 0 y, E 0 x not necessarily equal to E 0 y. In general they are different, but in special case they are same. And then we have cos kz minus omega t, and I add a phase over that plus phi. That is very important, because the component E and component, the x component of the E and y component of the, this x and y component of the E, they may not travel with a same phase. They can, there will be a, there may be a phase lag, and depending on the phase lag, actually it depends whether they will be forming a linear or circular polarization. So, this is the relative phase difference between the wave. So, this is the phase difference, relative phase difference, relative phase difference. This is the relative phase difference we are having. Now, if I plot how these things are working, let us plot it. So, and say this is the way Ex is changing, and I draw another this is the way EY is changing, but you can see that there is a constant phase difference between them, and that arises when phi is not equal to 0. If phi is 0, they will superimpose to each other, and that figure I will show. And if this is not, they will not superimpose to each other, there will be a phase delay. Now, if this is the general case, now what happen if when phi is 0 and or plus minus 2 pi n, 2 pi n, then these two waves are in phase. So, I can write my electric field in this way. E is equal to E0x x unit vector plus E0y y unit vector, and since the phase is 0 or 2 pi n, I can write it as cos of a common term, cos of kz minus omega t. Okay. So, how the figure will look like here, because they are now having same phase. So, the electric field, this is my y axis say, and this is my x axis, and this is the z axis. So, the x axis, it is a cos, it will be vibrating like this, and in y axis it will be vibrating like this, and this will be E y, and this will be E x, and the resultant will be the total electric field E. Now, if I imagine what is the resultant, we can see that. Let me draw here based on this figure. This is my y axis and this is my x axis, this is y axis and x axis. In figure 1, both are 0. So, I am going to get a tip here where the electric field is 0 at this point. Now, gradually electric field is increasing both for Ex and Ey. So, I am going to get a small increment here, and this is figure 2 with 45-degree angle. Then in another case, what happened, that it increases more in figure 3, then it increases to a maxima. That is precisely this point where we have E max, and the resultant E will be along this direction. This is the resultant E. Here in this point, the electric field will be like this and this, and the resultant electric field will be along this direction. So, let me go back to this. Now, what happened, this is case 4. In case 5, what happened, that this will go to 0 again, will be going down actually, it will go up and then it goes to 0, and then from the next half it will go to this direction and go to a maxima. So, from z direction we can see there is a vibration. From z direction we can see there is a vibration along 45-degree in this way. Along 45-degree or not, it depends on what is the amplitude of Ex and Ey, but it will vibrate in this direction. Since it is vibrating in one direction, we call this at linear polarization, or in short form it is called LP. In short form it is called LP. However, if the phase is no longer pi, then the scenario will be different, and this will be a different case, and here we call it as circularly polarized light. Circularly polarized light. So, again go back to our original expression. E, the electric field, is defined as Ex x unit vector plus Ey y unit vector, assuming the electric field is in xy plane. Now, Ex, this x component, I write E0 x cos of kz minus omega t. You can write sine of kz minus omega t also, and Ey will be E0 y cos of kz minus omega t and then a phase phi that we need to add. So, this is the most general expression of the electric field by dividing into x and y component, and x and y component are also a function of z and t, because this is a sinusoidally varying propagating field and we write this sinusoidal varying. Now, I put two conditions. One condition is here that E 0 x is equal to E 0 y to some value E 0, that is the condition 1 I put. This is very special condition that these two are same. And the second condition I put that phi is 2 m pi minus pi by 2, where m will be 0 plus minus 1 plus minus 2 etc. If that is the case, then my E x and E y I can write as E x is simply E 0 cos of k z minus omega t, and E y will be E naught sine of k z minus omega t. Now, instead of cos it becomes sine, and also E and E 0 x and E 0 y, they are same, that is the condition we put. Now, the total electric field, if I write the total electric field, if I write E, that will be simply E naught and then x cos k z minus omega t plus y sin k z minus omega t. So, that is the total electric field. Now, we need to understand what kind of electric field it is. Amplitude is same for E x and y component, but their variation is different, one is cos and another is sine. So, that means there is a pi by 2 phase difference they are having. So, if I draw these thing together, then for E y it starts from sine. So, I will going to get a sine function like this, but for cos it will be like it comes from the maxima and it will be 0 here, it going to maxima here at this point, it goes to 0 here. So, this is a cos function. So, this is E x and this is sine function, it will be E y, and there is a phase difference pi by 2 we are having. So, it is moving in this direction. So, if I take k common, then it should be z minus c t, where c is a velocity, omega by k, where c is a velocity, omega by k. Now, if I try to find in what happened in a 3-dimensional view, then Ey, so let me first draw, this is x, this is y. So the x component is a cos function, so it goes like this, and y is along y direction it is a sine function, so it goes like this. Goes like this. So here when we have a minima for x function, for y function, that is a maximum. So this is the way. So the resultant, now it is important to find what is resultant. So let me first, this is E of y and this is E of x. This is E of x, and along this direction it is moving. Now, if I calculate the resultant, then what happened? Let us quickly see. So, E x is equal to E naught cos of E naught cos of k z minus omega t, and if we have E y minus of E naught sine of k z minus omega t, this minus sign will come depending on the what phase value we are getting, what phi value we are getting. Suppose the phi value is such that we are getting this minus sign, then at z equal to 0, at z equal to 0 and at z equal to 0 plane over the time, if I want to find. So, at z equal to 0 plane we are looking, z equal to 0 plane, so this is when t is equal to 0. So, at t equal to 0, at z equal to 0 plane, for this condition what we get? We get that E x is maximum, that is E naught, but E y is 0. So, the resultant will be along this direction. This is the resultant electric field if the electric field distribution, x y distribution is like that. Now, what happened if I gradually increase the time, and when we increase the time, then E and when z equal to 0 plane, if I increase the time, then it should be sine of minus of omega t. This minus will come out and it will be plus, and then what happened that for increasing t, E x will going to decrease and E y going to increase. So, that means I am going to get a resultant somewhere here. This is at some point, say pi by 6 omega. Then I increase the T more and I put T equal to pi by 3 omega, and when I put T equal to pi by 3 omega, I can find what is the value, and if you do that you will find the resultant amplitude will be somewhere here. And finally, we put T equal to pi by 2 omega, that is omega t is pi by 2. When omega t is pi by 2, then the sine function will maxima and cos function will 0. So, I will get the resultant somewhere here, this will be my resultant. So, here you can see the tip of this arrow is moving in the left side, it is moving the left side. So, let me write down what is the Ex value here. So, at t equal to 0, Ex was E naught and Ey was 0. This case Ex was E naught root over of 3 by 2 and Ey was E naught by half. In this case Ex was E0 by 2 and Ey was E0 root over of 3 by 2. In this case Ex was 0 and Ey was E naught. Note, in all the cases the magnitude was E0. This is E0, this is E0, magnitude was E0 and this is E0. The magnitude is always E0. This is x axis and this is y axis on all the cases. So, this is for this kind of electric field distribution when E is equal to E naught x unit vector cos of, let us put at z equal to 0. Okay, let me write for the general one, then I will do that. Kz minus omega t and then minus y sine of kz minus omega t. So, this is called left circularly polarized light. This is called left circularly polarized light, and we can readily have with z equal to 0, the picture I had here, then E will be E naught x cos of omega t plus y sine of omega t, because there was a negative sign, that is why this will become positive, and it will move. So, if I draw a circle here, then this is the way the electric field will going to move. At this point it will be when t is equal to pi by 4 omega. At this point it will be pi by 2 omega. In a similar way, here we have, so it will over the time, here it is t equal to 0, starting from t equal to 0, the electric field will rotate along this left direction. So this will be 3 pi by 4 omega. This will be at pi by omega. The electric field tip here will come at 5 pi by 4 omega. Here it will be 3 pi by 2 omega. At this point it will be 7 pi by 4 omega, and again we will come back to this point when we have 8 pi by 4 omega or 2 pi by omega. So in this way we today understand how the electric field for circularly polarized light changes its direction, and in this case we find that how it is moving in the left direction. That is why I call the left circularly polarized light. Today I do not have any time to discuss more about the circularly polarized light. In the next class, however, we are going to discuss how the left circularly polarized light is the way the left circularly polarized light appear, how the right circularly polarized one can have by change the just by changing the sign, that is the phase. If I change the phase from positive to negative, then we are going to get the right circularly polarized light. So, with that note, I like to conclude today's class. Thank you very much for your attention and see you in the next class.